this case, first I'll talk about again the Rosenwick Mccarthy model. I'm little bit inclined to talk about this model repeatedly only for the reason that all the analytical results can be obtained explicitly for this model. And then yesterday I have discussed something about alley effect, and today I'll show you that once we introduce alley effect into the model, then how system dynamics will be in case of model including alley effect. And then I'll show you one simple model that produces very complex dynamics without going into much details. And finally, just as an example, one of our work in three species model, I just touch a little bit. So for bifurcation in Rosenwick Mccarthy model, as we have discussed yesterday, this is the basic model, and then we have this non-dimensionalized version. So we have three equilibrium points. One is 0, 0, this is 1, 0, and then x1 star, x2 star, which are given by this one. Now, if you look at the expressions for equilibrium point little bit closely, then immediately you can observe one interesting fact. The fact is that just try to think about what happens if your x1 star is equal to 1. So if your x1 star equal to 1, then this will be equal to 0, right? That means if we choose alpha, beta, delta in such a way that alpha delta by beta minus delta is equal to 1, then your x2 star equal to 0. And this clearly indicates that this E star coincides with 1, 0 whenever the parameter satisfies the restriction alpha delta is equal to beta minus delta. Once you have this kind of observation, then it is very easy to proceed further for appropriate bifurcation analysis. And what you have observed, that two equilibrium point coincides each other. This equilibrium point 1, 0 exists for all parameter values, and this equilibrium point exists whenever the parameter satisfies the conditions that beta greater than delta and x1 star is less than 1, because all the parameters are positive. So if these two conditions are satisfied, that is beta greater than delta and x1 star less than 1, then we can say x1 star and x2 star are positive, and hence they are components of a feasible coexistence equilibrium point. And you know that once we observe this kind of expression more carefully, like here I have mentioned we should have beta greater than delta, this also gives us some guideline that how to choose parameters. So it clearly indicates that if you choose delta as some value, then beta should be greater than that delta, because you need to have this equilibrium point as a feasible one. Then if you consider the restriction that x1 star should lies between 0 and 1, from there you will find another restriction on the parameters. So in this way you will get some idea about how to choose the parameter values. Now, as I have mentioned, that this system undergoes a transcritical bifurcation. In my yesterday's lecture, I talked about only analytical condition for transcritical bifurcation. Sorry, not yesterday's lecture, day before yesterday. Transcritical bifurcation for one-dimensional system. Now, for two-dimensional system, we need some additional results to ensure this undergoes a transcritical bifurcation. So additional calculations are, if you have a system like this, so let us think about in a general format, and this alpha is no way related to the alpha that I have mentioned in the previous slide. This is just a general system where alpha is the parameter. So then if you try to find out the equilibrium point, then you can find x star as a function of this parameter by solving this equation fx star comma alpha equal to theta 2 cross 1. And then if you calculate the Jacobian matrix, and finally we can demand that this system undergoes a bifurcation at alpha equal to alpha 0 and then x equal to x star, then couple of conditions are required to be satisfied. So one of such condition is this is equal to 0. So alternatively, we can say by solving the equation determinant of this quantity equal to 0, we can find out the threshold magnitude alpha 0. And once your determinant is 0 at alpha equal to alpha 0, this clearly indicates lambda equal to 0 is an eigenvalue of this particular matrix. And once if you consider this as a 2 cross 2 square matrix, then lambda is equal to 0 is a eigenvalue of this matrix as well as transpose of this matrix. So therefore, for df and df transpose, we need to calculate eigenvectors v and w associated with these two matrices corresponding to the eigenvalue 0. And then if you can verify these three conditions are satisfied simultaneously, then we can say at alpha equal to alpha 0 and x equal to x star, system undergoes a transcritical bifurcation. So these are shorthand mathematical expression, but their explicit expressions are given here. So W transpose F alpha, this means you differentiate F partially with respect to alpha. For this problem, we have considered F is a two-component column matrix. So therefore, F alpha means del F1 del alpha and del F2 del alpha. And then if you multiply it by W transpose from the left-hand side, so then you have this expression W1 del F1 del alpha plus W2 del F2 del alpha. And then for this second quantity, this df alpha, it means actually Jacobian matrix of F alpha. So these are the components of F alpha, that is del F1 del F alpha and del F2 del alpha. Now if you calculate its Jacobian matrix and then multiplied by V from right hand side, means this kind of inner product, and finally W transpose this one actually stands for this explicit expression. And in order to find out this one, here I have just mentioned what will be the expression for D2F of V comma V. This is given by this one. And if you look at this expression, then you clearly understand these two are nothing but the terms involved with the Taylor series expansion of the second order term, and variables are now replaced by components of this eigenvector capital V. So you can see this is a two-component column matrix, and our required quantity is W transpose this one. So if you consider its product with W transpose from the left, then you will have a scalar quantity, and you need to verify this is not equal to 0. Now the question is that how this kind of results can be applied in practical sense. So that means for a particular problem. So for that purpose, we consider this again Rosenwick Mccarthy model, and here parameter values are chosen except this beta. So that means we can consider beta as a bifurcation parameter. Now you can see, you know the expression for x1 star, this is given by this one, and then if you equate x1 star equal to 1 as I have explained earlier, so then you can find a value of beta, and that is nothing but beta 0 equal to 0.6. So the point is that from your observation, if you solve the equation that is x1 star is equal to 1, you can find beta 0 equal to 0.6. Alternatively, you calculate the Jacobian matrix of this system at the equilibrium point 1, 0, and then demand one of the eigenvalue should be equal to 0. That was the first condition. And as it is a upper triangular matrix, that is Jacobian of f evaluated at 1, 0 is an upper triangular matrix. One eigenvalue is straightforward is equal to -1. So there is no chance this will be equal to 0. So we are left with only one option, that this quantity should be equal to 0 in order to have this matrix as a singular one, and which gives beta 0 equal to 0.6. Once you have this value beta 0 equal to 0.6, you can substitute here, and then you find your capital V is this eigenvector, W equal to this eigenvector. But one question might be coming in your mind, that instead of this one, you may consider some other format. So whether the results will vary or not. Results will not be affected, because we are mainly concerned with the fact that some quantities are either equal to 0 or not equal to 0. Their magnitude does not plays any role in order to determine the appropriate bifurcation scenario. So that's why instead of this one, if you consider some scalar multiple of this vector, that will not alter your final result. So then based upon this function, you can see first equation does not contain beta, so its partial derivative with respect to beta will be equal to 0, but its partial derivative with respect to beta will be x1 x2 by this one. So that you have here f beta equal to this transpose. And having this f beta, now you can calculate d of f beta, as the first component is 0. So first two entries are exactly equal to 0, and second row entries are given by this one. And then if you calculate W transpose this one, you can find this is exactly equal to 0. Similarly, by calculating W transpose this quantity and W transpose D2F, you can find one of them is equal to this one, another one is this one, and hence the conditions which were required, that is first one is 0, second two are not equal to 0, they are satisfied, and hence system undergoes a transcritical bifurcation. And as I have shown you earlier, that this is the yesterday I did not explain that why it is happening at this level, and now you can clearly understand that your bifurcation threshold is 0.6, that is beta 0 is equal to 0.6. So therefore this axial equilibrium point 1, 0 is stable up to 0.6. After that it becomes unstable, and from where this stable coexistence steady state, this actually bifurcates from this one. So what we can say, that we can say that coexistence equilibrium point bifurcates from axial equilibrium point through a transcritical bifurcation. And again, this is the once more interpretation of the result. Once you can see that predator null line lies on the right hand side of the point 1, 0, so then there is no coexistence equilibrium point. You will have only 0, 0 as one equilibrium and 1, 0 as another equilibrium. Then at beta equal to 0.6, this line will pass through the point 1, 0. This is your transcritical bifurcation threshold, and further change in beta value, as you have seen in the bifurcation diagram, that for beta greater than 0.6 you have coexistence equilibrium point. So the line moves from this position to this position. Once you increase the value of beta above 0.6, and it will give you the appearance of this kind of equilibrium point. And for Hopf bifurcation, what we need to do, we need to find out the parametric threshold at which trace is 0 but determinant is not equal to 0, and also we need to verify that partial derivative of trace of this Jacobian matrix with respect to the bifurcation parameter, that is equal to 0 or not. If this is not equal to 0, then we can say this is a non-degenerate Hopf bifurcation. And then if you calculate the Jacobian matrix, and after evaluating this matrix and substituting the components of equilibrium points, and then if you solve, it will comes out to be a simple expression in terms of alpha. If expression is simple, then you can find out the value explicitly, otherwise you can have this result implicitly. So for Rosenwick Mccarthy model with same parameterization, if we now consider beta again as a bifurcation parameter, so then you can find that at beta equal to 1.2, the trace is 0, determinant is positive, and trace of this Jacobian matrix and its partial derivative with respect to beta is not equal to 0. So this ensures system undergoes a Hopf bifurcation at beta equal to 1.2, and that is quite clear here, because you can see for beta equal to 1, this is a stable equilibrium point. Then for beta equal to 1.25, that is just above the Hopf bifurcation threshold, your coexistence equilibrium point is stable and surrounded by a stable limit cycle, which is a magenta color closed curve that you can see here. And for bifurcation diagram, that means here you can see if you further change the magnitude of beta, this will size of the limit cycle keep on increasing. Now in the bifurcation diagram, what we plot, we have these two branches from where we can construct these bifurcation branches. The idea is that for each value of beta, that means you are taking increment of beta with a small amount. For example, say you are increasing beta with some increment 0.01. Then for each of those beta values, you are simulating this model. And once you are performing the simulation and you can ensure that initial transients are now swiped out and you are on the limit cycle. So then what you can do, you can collect the minimum value of x on this limit cycle and maximum value of x on this limit cycle, and you can collect them. Afterwards, for each value of beta, if you plot those maximum and minimum values of x on the limit cycle, then you can construct this branch as well as this branch. Just one information, if your numerical code is good enough, then only you can see this kind of parabolic like arc is emerging from here. Or otherwise, in various paper, you can see there is a little bit of gap. It shows some kind of conical structure instead of one curve is just completing here and changes its stability behavior, and from where another branch emerges strictly from this particular point. This completely depends upon accuracy of the numerical scheme. Now, bifurcation in a model with alley effect. Here, I'll just explain you with some graphical illustration that how you can understand different kind of bifurcation is possible. So in this case, if beta lies between 0 and 1, then it is called strong alley effect, and if beta lies between -1 and 0, then it is called weak alley effect. Now in this case, what will happen, you will find 3 equilibrium points on the axis. So on x-axis you can find E0, beta 0 and E10. Their stability properties are written here. You can have a look at it, and also you can consider these are your problems to find the answer that why they are stable and why they are stable or unstable depending upon this parametric restriction. So you can try to get mathematical support of this claim by working out these problems. And then for coexistence equilibrium point, we can have this expression. And for this model, fortunately, it is possible to find out all bifurcation scenarios or bifurcation conditions explicitly. There will be 2 transcritical bifurcation, and these 2 transcritical bifurcation thresholds are given by that means gamma TC1 equal to this and gamma TC2 equal to this. And again, if you solve the problem for Hopf bifurcation, then you can find this as a Hopf bifurcation threshold. Now, you may be wondering that why we have two transcritical bifurcation threshold here. This is only for the reason here you have two axial equilibrium points. One is beta 0, another is 1 0. But still your predator null line is a vertical straight line. So what will happen? In one case, vertical straight line passes through the point beta 0. In another case, vertical straight line passes through the point 1 0, and that will give you these two bifurcation threshold. And looking at the stability of coexistence equilibrium point, you can find this as the expression for Hopf bifurcation. And the results are summarized here. So this is the point when 1 0 is stable, then it loses its stability and interior equilibrium point has been emerged. Then within this small narrow range, there is a Hopf bifurcation, which is not clearly visible here, but that limit cycle is plotted on the right hand panel. That means if you zoom this portion, you can see this kind of structure, and you can understand that this bifurcation takes place over a very narrow range. That means when gamma varies from 0.35 to 0.354 something, because this point is 0.354, but this one is little bit more. If I recall correctly, the value was 0.35457, something like that. Sorry, 447, not 457. And these bifurcation diagrams are obtained for these parameter values with gamma as a bifurcation parameter. So after this Hopf bifurcation, what is happening here? Here you can see a global bifurcation. So that means this limit cycle disappear through a heteroclinic bifurcation, and then coexistence equilibrium point continues to be an unstable equilibrium point, and ultimately it will comes out to be this one and then disappear. So what happens apart from this small domain? So except for this small domain, all the time we can see that predator goes to extinction. But if your gamma value is greater than this threshold, then system shows a complete extinction, because this 0 0 is now the only attractor. And therefore, if you look at some of the phase portrait, so this is the phase portrait before first transcritical bifurcation threshold, when your 1 0 is stable as well as 0 0 is also stable, and this stable manifold of this axial equilibrium point beta 0, that plays the role of separatrix between the basins of attraction of this equilibrium point. Now, when gamma is greater than this transcritical bifurcation threshold but less than this Hopf bifurcation threshold, then your coexistence equilibrium point is stable. Again, there is a separation between their basins of attraction. Still, there is a wide domain from where, if you start, trajectory will converge to the extinction equilibrium point. Then once you have your bifurcation parameter value between Hopf and homoclinic bifurcations, then you can see this coexistence equilibrium point is unstable, but surrounded by a stable limit cycle, which is a green closed curve. And after that, this is the homoclinic bifurcation threshold. You need quite patience in order to determine appropriate value correct up to this many decimal places. I'm just showing you only for the reason to give you some sort of confidence these are doable. These are not something like that, okay, it has been done by this person, it is too much difficult. Answer is no, this is just a question of patience. So what is the concept of heteroclinic bifurcation here? That once the size of the limit cycle keep on increasing with the further change in gamma value, ultimately what will happen, this limit cycle will pass through these two equilibrium points. So there will be one arc which is starting from this point and converging to this one, and there is another arc which is starting from this one and converging to this way, and this is called heteroclinic cycle. And after that, we can find these two type of situation. So in both these cases, both the situation we have some sort of extinction scenario. But what is the fundamental difference here in these two phase portrait? Here you can see the coexistence equilibrium point, but here we cannot find any coexistence equilibrium point. So here we have a coexistence equilibrium point, but it is stable, and here we don't have any coexistence equilibrium point. Now we consider another model. I should not go into the detailed bifurcation analysis for this system because system dynamics is quite complex. So this is nothing but a modified problem where the functional response depends upon both prey as well as predator density, and okay, this is not for me. I thought some questions are there. So this is the ratio dependent functional response, and here what we are considering that there is a intraspecific competition among the predator. So that's why apart from this linear death rate, there is a quadratic term which represents the intraspecific competition term. If you want to have more details about this model and its analysis, you can have a look at this paper. This is completely taken from this paper only. And you know that this model actually undergoes this long list of bifurcations: saddle node bifurcation, transcritical bifurcation, Hopf bifurcation, Bogdanov-Takens bifurcation, generalized Hopf bifurcation, homoclinic bifurcation, as well as heteroclinic bifurcation. Now the question is that how we can speculate that this much of bifurcation can occur. So in order to get answer to that question, you need to look at the equation of non-trivial null cline. So non-trivial null clines are nothing but the equations except the u factor from the first equation and equation of the curve except the v factor from the second equation. So that means from here, if you factor out u, and from this equation, if you factor out v, and then you solve first equation for v and second equation for u, then you will find this explicit expression. Then looking at the equation and depending upon the magnitude of the parameters, you can understand what kind of curve they represent. But in order to find out the coexistence equilibrium point, what you need to do, you need to eliminate v between these two equations. So that means here you have v explicitly in terms of u. In the second equation, you have u explicitly in terms of v. So what you can do, you can substitute expression of this v in terms of u in this equation, and then you will find a cubic equation. And once it is a cubic equation, this is a quadratic equation. So then you can clearly understand that there exists at most two point of intersection between these two curves, because these can admit at most two real roots, and corresponding to those two real roots, you will have the corresponding v components of the coexistence equilibrium points. But the idea is that depending upon the parameter, there might be one feasible equilibrium point, there might be two feasible equilibrium points. And here I can show you in the next slide that in this case you can find only one point of intersection. But how this kind of structure are coming into the picture, if you look at the first equation, then if your alpha greater than 1, then your denominator is positive. But if your alpha less than 1, so then there is a possibility that u equal to 1 minus alpha is an vertical asymptote. And interestingly, if alpha is equal to 1, then this is 0, this u cancels with this one, and you will have a simple state. So what will happen, that depending upon the parameter values, you can find different possible shapes of the null clines. So in one case, you have these two shapes of the null cline which intersect at a unique point, and in this case we can find unique coexistence equilibrium point. Again, you can have this kind of structure for prey null cline and this kind of structure for predator null cline. There is one point of intersection, but in a particular situation, you can choose the parameter values in such a way that apart from the origin, these two curves intersect each other at two different points. And how it can happen? So one possibility is that these two equilibrium point coincides and disappear. So that means instead of having this structure, you can start bending this curve in such a way it will take a form like this. Now, before taking this kind of form, what will happen in between? It will pass like this, then crosses this curve, again crosses this one, and it will create 2 point of intersection. And as a result, if you look at the bifurcation diagram, so this kind of complicated bifurcation diagram you can have. So these bifurcation curves are actually divides the parametric plane into 8 different domains. But you might be wondering that why I am not saying anything about details of the bifurcations, or why I am not showing you the equations of the bifurcation curves. That is only for the reason that in this case you cannot find any one of them explicitly. Rather, there is a implicit expression, and by some numerical technique we have plotted this curve in order to have this schematic bifurcation diagram. But what I'm going to show you, I can show you that how dynamics of the system changes if we take parameter values from different domains that is shown here. So just for your information, this is a boundary. On the right hand side of this line, there is a possibility of existence of 2 equilibrium point. On the left hand side of this line, there is always 1 equilibrium point. Then this magenta color curve is the saddle node bifurcation curve. This green color curve is the global bifurcation curve, and blue color curve is the Hop bifurcation curve. Hop bifurcation curve and saddle node bifurcation curve, they intersect at a point which is called Bogdanov-Takens bifurcation point. And from that point itself, there exists a global bifurcation curve. In this case, it is homoclinic curve until it does not intersect this vertical line. But after this point, it becomes a heteroclinic bifurcation curve. And on the Hop bifurcation curve, you will find a generalized Hop bifurcation point. It means on the one side, you will have stable limit cycle. On the other side, you will have unstable limit cycle. And these are the phase portrait for different region. In R1, you can find this is stable, and at the same time origin is also stable. So their basins of attractions are separated by these separatrix. Then if we go to the bifurcation domain R2, so that means now we move from this domain to this domain. If you choose parameter value from this domain, then you can find that unstable equilibrium point surrounded by a stable limit cycle. So limit cycle is stable, equilibrium point is unstable, so therefore Hop bifurcation is supercritical. Next, from R2 we can go to R3, or you can think about that you are moving from R1 to R3. Now if we go to R3, then what you will find? You will find stable limit cycle that is surrounded by an unstable limit cycle. And this is the beauty of this analysis. Now you can see on this part it is stable limit cycle, on this part it is unstable limit cycle. So this branch of the Hop bifurcation curve is the subcritical Hop bifurcation curve. On this part it is actually supercritical Hop bifurcation curve. Then if you go to R4, then you will find this one is unstable equilibrium point, and all the trajectory they actually converge to the extinction equilibrium point. Now if you choose a point in R5, then you can see that all the trajectories they are converging to the extinction equilibrium point. But what we have 2 unstable equilibrium points at this particular location in R6. So R6 is here, so that means above the saddle node bifurcation curve, because below it there is no such coexistence equilibrium point. So phase portrait will be more or less same as R4. So that's why we can discard this region. Then from R6 to R7, if we move to R7, so then you can find that equilibrium point that is surrounded by an unstable limit cycle. And here you can see the presence of second equilibrium point. So now we are in a domain. That means we are in domain R7, which is on the right hand side of this point. And again, this Hopf bifurcation curve is subcritical. So therefore, we have unstable limit cycle surrounding the stable equilibrium point. And then if you go further, so that means if you move to region R8, then you can find this equilibrium point. This is stable. So what we can see here, that mainly above these curves, there is a stability, but below this one, there is extinction. And finally, this is an interesting picture, that is the existence of two limit cycle. This bifurcation diagram I have not shown to you, but what happens that this case, what we have, stable equilibrium surrounded by an unstable limit cycle, and that is surrounded by a stable limit cycle. So one question might be appearing in your mind, from where I am talking about the existence of two limit cycle. If you look at our paper or in the literature very carefully, then there is a very small domain around this generalized Hopf bifurcation point. Sometimes it is also called Boutin bifurcation point. So around this point, there is a small parametric domain within which you can find two limit cycle. Now, from where they are generated or through which they disappeared, this is actually a parametric domain in the vicinity of GH point, where you can see two limit cycle. One of them is stable, another one is unstable, collides and disappear through the saddle node bifurcations of limit cycle. So I have talked about saddle node bifurcation of equilibrium point, but just to motivate you, or rather as a stimulus, I took this example to give you some idea that not only saddle node bifurcation of limit cycle, rather saddle node bifurcation of equilibrium point, saddle node bifurcation of limit cycle is also possible. And here you have this unstable limit cycle. This can coincide with this one, so that means this touches this point, which will produce the homoclinic orbit, and then you have stability here. So now we come to a little bit discussion about the a three species model. So here what we have considered a very simple model. You can see most of the terms are polynomial, but initial 2 points are nonlinear term. This work was carried out with Professor Takauchi during my visit to his university for a couple of days. And then what we have thought, our main criteria was, or main target was, to come up with a model which looks like very simple, but its dynamics is quite complicated, or rather quite complex. So here I am not going to show you any story, rather a little bit complicated bifurcation diagram, and you can see that entire parametric domain can be divided into 17 different regions. So this is the credit of my PhD student Moitri Sen. She did this calculation and to come up with this kind of bifurcation structure. And also we have identified different possible bifurcation scenario. And in our paper, you can see all the expressions implicitly for these bifurcation curves are given. And this is not the only bifurcation diagram. If you change some of the background parameter, other kind of bifurcation is also possible. But what I'm going to emphasize here, at the organizers asked me yesterday about period doubling bifurcation. So here I can talk about a new kind of bifurcation that we have introduced in the area of mathematical ecology, that is peak adding bifurcation. So apart from period doubling, this is a newly emerging area. Of course, very few papers have appeared so far, but sometimes your model is have such kind of nonlinearity which can leads to peak adding bifurcation. how it takes place. So here you can see a periodic behavior, and then with the change of parameter, you can see two periodicity has been appeared. So you have two sets of local maxima and two sets of local minima. And as a result, system changes from this kind of one limit cycle to two limit cycle. This is period doubling. But afterward, what happens if you keep on increasing the parameter? So there is no further separation. So it is not going from 2 period to 4 period or 8 period or something like that. Instead, what we can see, some kind of point of non-differentiability that appears here, and we have investigated what is the phenomena involved with the system, or what is the mechanism which is responsible for generation of this kind of point, which seems to be a point of non-differentiability. Then what we have observed, that if you keep on changing the parameter value, you can see some sort of distortion at this part of the time series, and at a particular threshold you can see, if you have a close look at it, then you can find out this is a point of inflection. And after this point of inflection, what will happen? Two new local maxima and minima are actually appeared. So earlier case, what happens, that there is a difference in the height of the peak which generates the period doubling bifurcation. But here, through a what I said, I forgot. That is through point of inflection, two new local maxima and minima have been appeared. And if you proceed further, then you can see their height and depths are keep on increasing. But after some time, what you can observe, that is another interesting phenomena. So there is a variation in the heights of AB. So that's why one set of local maxima minima here are labeled as AB, AB, and another set is labeled as A dash, B dash, and A dash, B dash. So what we can say, that just due to appearance of a point of inflection, and then you can see the generation of new peak or appearance of new peak. So that's why it is called peak adding bifurcation. And this is all about my talk. And lastly, I must thank this person, Vitaly Volpart, who actually dragged me to work in different area. And yesterday you were talking about my papers and speed of the work. I know how to express, but I have started working with him from 2015. There is a long story. I made a blunder in 2009, but from 2015 we have started working with him, and by this time, if I recall correctly, we have completed at least 19 to 20 papers with this person in different areas. And these are my other collaborators with whom I have worked on different type of problems, but mainly with these persons I have worked on that is temporal model. But Vitaly is mainly interested with the spatiotemporal model, and it was some sort of our fortune to have a paper where we have shown through mathematical modeling that how Darwin's evolutionary structure can be generated through mathematical modeling. Thank you very much for your attention. And I would be happy to have receive some question and discussion, comment, suggestion, whatever you have.
Participants, any questions? Thank you, sir. Thank you very much for this. Yes. Go ahead.
Good evening, sir.
Yeah.
Sir, the last model, the multi-species model, is there any work done on this model regarding fractional calculus?
I think no. But I have a little bit reservation about the fractional calculus model, but recently we come up with one paper in that direction. You know, from basic assumptions, that means mechanistically it is not well-known method to derive the fractional derivative model, because if you start with some assumption, so mechanistic assumption, you can derive ODE model, you can derive PDE model, you can derive delay differential equation model, stochastic differential equation model, reaction diffusion equation model. But I have not seen many work or any concrete work in the area where the fractional differential equations are derived from the basic assumption. Because you can recall in my yesterday's lecture, I just explained that how ordinary differential equations are constructed. So similarly, for different things, that is delay, then stochastic model, then reaction diffusion model, we can find out the mechanistic derivation. But for fractional differentiation, I'm little bit conservative in that sense, because still I don't have any clear-cut idea that from which assumption, because most of the time people writes, okay, we can replace this derivative, that means can be replaced by fractional derivative. But my question is why? But that means how can you derive this equation explicitly? If you find any literature, please forward it to me. I'll be happy to have a look at it.
Yes, sir. Because there's a model by Lotka Volterra that is also a 3-species model.
Yeah.
Integer order. But I have seen work that the corresponding fractional calculus model. Some people have done it. So that's why I ask, is there any possibility of having the same?
Yeah, because one can study, but always I am looking for ecological justification. That is the main part. Because if you cannot derive the model mechanistic way, I don't know, I can find out the slide or not, but if time permits, I can show you some of the derivation for PDE model or something like that. I think Mr. Rajaji wanted to ask
sir.
some
Yes, he has posted one question. He has said which kind of numerical schemes used in continuation to this fractional model.
In fractional model?
Or maybe, sir, I'm asking him to unmute your, please, Dr. R. Rajaji, unmute yourself and ask the question directly. It'll be better. Hello? Please unmute yourself. You can. And ask your question. He has just posted this question that which scheme, numerical
in
scheme.
In case of bifurcation diagram that I have shown, in all the time I have used RK4 method. But the most important part is that choice of delta t and the number of iterations is required to obtain result which are free from transient dynamics.
I think it should be clear to him now. Anyone else wants to ask some question? Any other participant? Sir, in that 3-species model you have just discussed in the last, is there how we have formed the equation? That was not clear. We just got the equation from you only, and it was not. I want to know what are the parameters you have taken, how we can per capita or something like that. We use in a 2 prey 1 predator model. Even it is in our syllabus also. So just I want to have a clarification on that. This you have taken beta 1, this may be, and this is alpha, and this is epsilon alpha 1. So just explain a little bit, because you have just given the values.
Yeah, the point is that if you substitute alpha 1 equal to 0, this will become beta 1.
Okay, then that the growth rate, you can say.
Just a minute. You will get beta 1.
Okay.
Then if you substitute alpha 2 equal to 0, you will get beta 2.
Yes.
So then alpha 1 and alpha 2, these are, if equal to 0, then this is nothing but classical Lotka-Volterra
Yeah, Lotka-Volterra.
two-prey one-predator model.
Yes, yes.
And this model was explained in detail in the book by Professor Takauchi. Now you forget about this jet component. You forget about this jet component. So in this case, what does it mean? You can see that once x approaches to 0, once x approaches to 0, just look at this particular term. So this term approaches towards the value 0, right? So in that case, if x approaches to 0, whatever may be the value of alpha 1 and beta 1, once they are positive, this is approaching to 0. So that means their intrinsic growth rate is negative.
Yes, sir.
Right? So that means they suffers from alley effect. This is an alternative modeling approach just to take care of the fact that this is actually called alley effect due to insufficient mating success. And I can try to give you a rough idea. Suppose we have one population that is divided into two groups, that is male and female. Okay. Once it is divided into male and female, then you can divide each of them into 3 age groups. So that means juvenile, then adult, and then old. So that means it is divided into 3 groups depending upon their reproductive ability. So one group before reproductive ability, one group within reproductive ability, another group after reproductive ability. And then if you mechanistically consider that what is the frequency that one eligible male individual with interact with one of the female eligible individual, and that mating leads to successful birth of newborn individual, from there you can actually find out this functional form which can model the alley effect in both the species growth. But the point is that depending upon the characteristics of the species, their intensity of alley effect. So that means for some species, maybe 20 individual is sufficient to grow further. For another species, maybe 40 or 60 individuals is sufficient to grow further. And that's why we have used 2 different parameterization in order to come up with this kind of alley effect. So now just if you forget about this y and z term and look at this particular expression, so this is some sort of increasing curve. It is starting from 0, increases with x, and then saturated at some value. And this one is a straight line. And therefore, you can probably try to understand that there is a point of intersection between this curve, that is beta x1 by x plus alpha 1 and 1 plus x. And depending upon their number of point of intersection, it will give you the threshold, like whether it is a weak alley effect or strong alley effect. If one point is negative, another point is positive, so alley effect is weak. And if one point is both the points of intersection are positive, so then it means it is a strong alley effect.
Yes, sir, it's fine. But sir, can we take x is equal to 0? Can we assume, because x is the density of this, I think, prey you have taken, or and y, and also prey and predator is z.
Yeah, the point is that 0 means we are just trying to think about once you are
one that means 0. 1 prey.
Yeah. Yeah, definitely you can consider one prey, but
and there's one prey and predator.
One prey predator model is already studied by Mura
yes,
and others.
Yes. Yeah. Okay, sir. Thank you very much. Anyone else has any question? Anyway, sir, it was really very enriching and valuable information on bifurcation in RM model and with alley effect, with complex dynamics model, with complex dynamics and 3 species model. We had really an enriching time with you. And moreover, we are really inspired by your growth story. you explained yesterday also, it is really inspiring. So we are very much grateful to you for taking time out of your busy schedule to be a part of this workshop and to share your expertise with the participants.
Yeah.
We
Actually,
all have gained valuable insight about all the concept of the topics explained here. We hope it was a positive experience for you as well. I
yeah,
think you were a good audience.
yeah.
The information you shared was really very enlightening. Again,
Yeah.
our sincere thanks for supporting this teachers enrichment workshop with your valuable lecture series. We hope and wish to attend your lectures very soon in near future. And please
Yes.
inform us if there is another lecture series going on and you are participating. We'll love to attend that. Only
Yeah,
just we'll be attending. We don't want
Yes,
any
sir.
certificate for
Sure,
that.
sure.
I actually love to deliver this lecture only for the reason because during COVID I was under a little bit of trauma. You can't believe. Probably if I count the number, I have delivered more than 37 lectures on COVID epidemic. Each and everyone started asking me, say something about COVID, say something about COVID.
Yes.
And actually, before that, I never worked on epidemiology seriously. But this person, that's why all the time I thank this person, Vitaly Volpart. He dragged me some way that Malay, there is no way you have to start working on this problem. And then I said, I never worked on these things. Then he said, okay, you can start helping me. You don't need to work anything. So ultimately, I started learning something. We had several discussion over Skype, and all the time his only question was, Malay, when again we can meet physically? Okay, let us wait for some time and let's see. He actually visited our campus twice, and he's an excellent scientist. You can't believe his level of knowledge and depth. I think there is another question from Mr. Rajaji. Does nonlinear model and corresponding linearized model have same qualitative behavior? Yes, answer is that, as I have mentioned earlier, in the vicinity of the equilibrium point, not beyond that. So if it is around some global bifurcation scenario, then linearized model cannot say anything about the global bifurcation. This is a very good question, that whether nonlinear model and corresponding linearized model have same qualitative behavior. Yes. I like this question.
Thank you, sir. Thank you very much.
Thank you, sir.
So, anyone else? Any question? So once again, sir, of course, we don't have special words to say thank.
No, that is
really
not
it was really very nice, and moreover, you have shared all the talks right on this platform. That's also very remarkable.
Yes.
Because sometimes we ask and it gets time to get the talks. You have shared first of all, you have shared, and then you have started teaching us. So it was really helpful because we can go through.
There is one comment from Sushil Kumar.
Sir, so many are writing. Thank you.
Yeah, that you did on lockdown. I must clarify, that is not work on lockdown. Rather, that was some sort of explanation. Could you please allow me for 2 minutes?
Yes, sir. Sure,
sure, sir.
So I can quickly show you our work on that particular COVID. And this we have predicted in
by data analysis, I hope.
Yeah, that is June and September. Then reviewers were not that much happy, but ultimately this is the true scenario, and that we have predicted a long back, and that is some sort of interesting part of the story. I just share my screen and quickly I can show you this one. Can you see my
yes,
screen?
sir. Yes, it's visible.
Okay. So now if you look at this part, that is
zoom, please, sir. Zoom it a little bit.
Okay.
Yes, sir.
Now
it's okay.
So first of all, this is a horrible model, because you can see this is the complete description of the model. And this is the some sort of schematic diagram. But main outcome was that during June, July, we have predicted that if we should not follow all the guidelines, then there is a chance that second wave will be much more higher compared to the first wave. This was the main contribution.
It's true now, we can see.
And at that time, reviewers were not very much happy. But fortunately, when the deadline was to submit the review report, by that time, at some places, second wave have already arrived. And then we matched with the data, and we have shown that in case of Spain, you can see that second wave is much higher compared to this one. But the point is that according to my personal understanding, still I am fighting with Vitaly. This is not the second wave, because if you talk with the top level doctors, then you can understand literally second wave means if there is a growth in the epidemic in a situation that at least for 1 week there was not a single case. And that is the main mistake is made by most of the people. So this is not the second wave, rather it is crunch for invitation, and I get a chance to talk about something else apart from COVID. So nowadays, if anybody asks me to talk, give any talk, first I ask if it is not on COVID, then I can deliver a talk.
Sir, I have a question.
Yeah.
The paper, the model which you have shown, is it a chaotic model?
No, not chaotic.
Not chaotic.
Because in this case, you can prove that it satisfies monotonicity property. So your speculation is one hand is absolutely fine, because you can see so many equations are there, then why there is no chaos? There is no chaos because it is a monotone system.
Okay. Because we can see that COVID is creating a chaos all over the world. So I'm interested, or I want to make a model which will be chaotic.
But from time series, you cannot see any kind of chaos as of now.
Yeah,
as of now, because
I have worked on 2-3 models, and I see this that they are not coming out to be quite chaotic by calculating the Lipnov exponents and all.
Yes.
But
because
sir,
time series shows, because what is happening that sometimes I also received some papers from different journals to handle. They have talked about chaos, but the idea is that it seems to be chaotic, but that is happening, that some kind of jump or some kind of irregular growth or decay that happens just due to emergence of new viral strain. So that is not at all chaotic.
Okay. Thank you, sir.